Some foods remain hotter much longer than others do. The filling of hot apple pie may be too hot to eat even though the crust is not. The pie filling takes longer to cool than the crust. Different substances have different capacities for storing internal energy. It takes nearly 20 minutes to bring the water in this pot to a boil. For an iron pot alone, with the same mass as the water, it would take only 2 minutes to reach the same temperature. And for a silver pot, also of the same mass, only about a minute. Why do different materials require different amounts of heat to raise temperatures? The answer is that different materials absorb and store internal energy differently. That internal energy can be partly potential energy associated with interactions among particles, which is large for solids and liquids and small for gases. The other part of internal energy is kinetic energy of the particles in the material. This kinetic energy comes in three main forms: the energy of to and fro translational motion of particles, the rotational kinetic energy of particles, and the vibratory motion of particles. How energy is divided up within a substance varies greatly from one substance to another. Water absorbs about 9 times as much heat as an equal mass of iron for the same increase in temperature. We say water has a higher specific heat capacity, which we'll simplify as specific heat. The specific heat of any substance is defined as the quantity of heat required to change the temperature of a unit mass of the substance by 1 degree. So whereas 1 gram of water requires 1 calorie of energy to raise its temperature 1 Celsius degree, iron requires a fraction of this, 0.108 calories, to do the same. We can think of specific heat as thermal inertia. Recall that inertia is a term in mechanics to signify an object's resistance to a change in motion. Specific heat is similar in that it signifies a substance's resistance to a change in temperature. Let's focus on water, which has a much higher capacity for storing energy than most materials. Because water absorbs a large quantity of heat for a correspondingly small temperature rise, it's a very useful cooling agent in the cooling systems of automobiles and other machines. If a liquid of lower specific heat were used in cooling systems, its temperature would rise higher for a comparable absorption of heat. The tendency of water to resist changes in temperature affects climate. On a world globe, notice the high latitude of Europe. Europe has the same high latitude as northeastern regions of Canada. They both receive about the same amount of sunlight per square kilometer. But winters in Europe are much milder than winters in northeastern Canada. Why? Simply put, water's high specific heat. The Atlantic current, known as the Gulf Stream, carries warm water northeast from the Caribbean. It retains much of its internal energy long enough to reach the North Atlantic off the coast of Europe, where it then cools. The energy released, about 1 calorie per degree for each gram of water that cools, is transferred to the air, where it is carried by the westerly winds over the European continent. Europeans hope that this continues. A similar effect occurs in the United States. The winds across North America are largely westerly in direction. On the west coast, air moves from the Pacific Ocean to the land. Because of water's high specific heat, water in an ocean doesn't vary much in temperature from summer to winter. Water is warmer than air in the winter and cooler than air in the summer. In winter, water warms the air that moves over it, and the air warms the west coastal regions of North America. In summer, water cools the air, and the west coastal regions are cooled. On the east coast, however, air moves from the land to the Atlantic Ocean. Land with a lower specific heat gets hot in the summer and cools rapidly in the winter. So due to water's high specific heat and a westerly wind, the west coast city of San Francisco is warmer in the winter and cooler in the summer than the east coast city of Washington, D.C., even though both are at about the same latitude. I want to leave you with 2 questions. Number 1, which has a higher specific heat, water or an iron pot? Defend your answer. Question number 2 pertains to the next lesson, in which we'll consider an iron ball and iron ring. The ball can snugly fit through the ring when both are at the same temperature. If the ball is heated, it will expand and won't fit through the ring. Here's my question. When only the ring is heated and expands, will the ball be able to fit through it? Think about that. Until next time, good energy.